Good morning, everyone. My name is LJ Miranda from AI2, and I'm going to share our system that we submitted to the SIGTYP 2024 shared task. So first, the problem statement. We chose to work on the constraint task, which requires us to build a system for parts of speech tagging, morphological annotation, and lemmatization. The dataset is also from the shared task organizers. It contains a mix of Universal Dependencies data and some Hungarian codices. There are 13 language overall from 4 language families and 6 scripts. And finally, it has 2.6 million tokens for training and around 300,000 tokens for validation and testing. Our general approach consists of two parts. First is pre-training a transformer-based multilingual language model or LM on the shared task tokens. Here, the input would be the texts from UD, and then we learn an unsupervised training objective, and then the output is a pre-trained multilingual base model. And then we fine-tune it on the UD annotations of each language. So the input would be the label data, and then we train a supervised learning objective to fine-tune a model per language. So the final artifact would be 13 multitask models because there are 13 languages. Before we continue, I want to talk about related work. The idea of multilingual pre-training is not new. Some premier examples include XLM Roberta and multilingual BERT, which were trained on hundreds of languages. And it has been shown that multilingual LMs are quite good, especially in zero-shot cross-lingual transfer. However, the majority of these models were trained reasonably so on modern text. Personally, one reason why I got interested in this shared task is because it's a nice way for me to try something different and pre-train an LM from, you could argue, domain-specific text. What is also interesting is that there are few multilingual LMs on historical and ancient language data. The most notable example I could find is HMBERT. There are also some Persian spacey models, but aside from that, not much. Most LMs are language specific and mostly focusing on name entity recognition as their downstream task. So for model pre-training, there are 3 major steps: building the pre-training corpora, setting up the architecture, and the pre-training proper. First, we use the tokens from the UD corpora to construct the pre-training corpus. Initially, we experimented on different sampling techniques to balance our dataset. One way we approach this is by upsampling other languages based on the number of tokens. So what we did is we augmented the dataset for different levels and types of upsampling and pre-trained as a test for 20,000 steps. We then tracked the pre-training and validation loss. However, we noticed that this made the pre-training quite unstable with little to no validation accuracy gain. So in the end, we actually just stuck with a default data distribution. For the pre-training architecture, our overall configuration resembles that of XLM Roberta. We also took inspiration from the HMBERT paper and trained variants with different numbers of layers and parameters. And we mostly use these smaller variants as testing or as sanity check, but the final submission is based on the base variant of the model. And then for the pre-training proper, we use the byte pair encoding as our tokenizer, and we trained the model for 100,000 steps with a linear warm-up for the first 12K steps. Then we proceed with model fine-tuning. There are also 3 steps. The first is preparing the dataset, then setting up the architecture, and the fine-tuning proper. Preparing the dataset is straightforward. We converted the conlu files into spacey doc objects. It is a special type of data that is useful for the spacey library. We also ensure that we preserve the tokenization when converting into this format because spacey itself has its own tokenizer. And then for fine-tuning, we use the spacey library. At a high level, what happens is that we access the contextual embeddings from the pre-trained LM's last hidden state, and then we pass these embeddings as additional input to our downstream task-specific network. The good thing about spacey is that the resulting model or pipeline is multitask so that the training can be done in parallel. So each pipeline can actually do pause tagging, morphological annotation, and lemmatization, but the final artifact is just like one file that you can download. I also want to spend some time talking about the architecture of our fine-tuning network. The setup, as you see on the right, is quite straightforward. Again, we pass the pre-trained embeddings to a linear layer, then followed by a softmax layer to obtain the logits and eventually the class probabilities. Then the loss function is minimizing negative log likelihood. What only differs for each task, that is in parts of speech tagging, morphological annotation, is what the classes represent. So what do C1 to Cn represent? For the parts of speech tagger, the class labels are the set of all parts of speech tags for a given language. So it would become a multi-class classifier that predicts a vector of tag probabilities for each token. And then if we want to predict the proper tag for a token, we just get the argmax. For the morphologizer, it's a bit different. Here, what we do is we treat every unique combination of morph features as a single class. So we didn't model each feature individually because that would be costly, especially if we have 13 languages. So we focus on just using the label combinations. And it also allows us to train in parallel and much more efficient. The only limitation is that it won't be able to predict unseen combinations in the training set. So if a unique combination in the test set exists, it will not be found because the classes do not represent that. The lemmatizer also follows a similar approach, but here we're using a neural-based edit tree lemmatizer from Muller et al. So each class is now a set of possible edit trees. One thing you can think of edit trees is it's a recursive algorithm that derives the lemmatization rule or a set of rules given a token lemma pair. So for a decent sized dataset, you can actually generate hundreds of edit trees. So the classifier's task is now to determine the most probable edit tree for a given token. So if the most probable edit tree can't be applied to the test token, we then back off to the next probable tree and so on until we reach the token's surface form. I also want to share some alternative configurations that we tried. One is to fine-tune on the combined dataset, that is a single monolithic model, versus fine-tuning language-specific models. Our findings suggest that fine-tuning per language leads to better performance, so we actually stuck with that. The next thing that we did is we tried to replace the pre-trained LM and with the Spacy's default word embedding algorithm. The way it works, the way the hash embedding works, is that we get lexical features for each token, such as the prefix, the suffix, and the shape, and then we hash them multiple times to create an embedding table. Ideally, this is more memory efficient since it's a lookup table compared to like the dynamical computing done by the transformer. But here we stuck with a transformer-based pipeline because it performs better. And I think at this point, we don't really care about efficiency. So we scrapped the hash embedding idea. So at the end, we fine-tuned 13 multitask models using this configuration. On your left, you'll see the hyperparameter settings. We use the common defaults, such as the byte pair encoding for the tokenizer, an add-up optimizer, and a relatively small learning rate. We also use a linear warm-up for the first quarter of training just to help it converge. And on the right, you can find the resulting Spacy pipelines. This would be the output artifacts that would contain the multitask pipelines for our 3 tasks. So as for our results, we compared it against the baseline. So here, we just copied the results from the leaderboard in Codalab. We highlighted scores where we beat the baseline in green. And it shows that for parts of speech tagging and morphological annotation, we performed decently well, but not so much on lemmatization. As you can see, we only beat the baseline for medieval Icelandic and the 2 forms of Latin and classical Chinese. What I did was we inspected the resulting edit trees, and I think one big issue is the script itself. Classical Chinese is actually more of an outlier because the token lemma pairing is more straightforward. So for example, the delta for Gothic and Old French with respect to the baseline is quite small. They're in Latin, but for others, the margin is quite wide. So the edit trees, what would happen is that they split with respect to the longest common substring. And that kind of works on Latin scripts, but it doesn't transfer to others. Sometimes, for other scripts, the longest common substring is 2 characters long, and that's not enough, or it's not very informative for splitting or making out the rule. So we also look into the performance and the validation set. Here we use the F1 score for all tasks. The results are quite decent, but you might notice that the performance on Coptic and Ancient Hebrew is drastic because our pipeline cannot handle multi-word expressions. So for some background, in the shared task, we also need to provide annotations for these subtokens. But if I have to do it using our contextual embeddings, I need to substitute the subtokens on the full expression. But that would result in grammatically incorrect text, and that would give some worse results overall. That's actually one of the limitations of this work, but the solution is really straightforward. It's just a matter of aligning these tokens properly. But for the time being, I got short on time, so I wasn't able to implement that. Finally, we also look into cross-lingual transfer on the cross-lingual capabilities of our model. The question here is to see if a model from one language is transferable or it would work on another. Here you'd see a matrix where we map each source language to a target language, and we compute the F1 score in the development set. The results aren't too surprising. Classical and late Latin and medieval Latin have decent cross-lingual performance, and that's expected because the latter is a direct continuation of the former. So one could argue that there's a huge overlap between these two languages. In addition, languages in the Indo-European family have decent cross-lingual performance with one another, and we can see this in Old Church Slavonic and Old East Slavic. One could also argue that the script and the language family is a big factor for this transferability, and we hope that this is just one small evidence to support that. Personally, I did this because it is very interesting to see the same method applied to historical languages, and I think it can have some applications not only in this domain, but also in low-resource data. Before we end, I want to talk about some limitations and challenges for our work. First is the pre-trained LM size. The model that we submitted is equivalent in terms of size to Roberta base. We would love to have trained a larger model, but there's definitely some computing constraints that hindered us to do that. Second, for the morphologizer, we treat each label combinations as its own class, and we can only predict the scene combinations during inference. One way to solve that is to model each label separately, but with 13 language in the shared task, it might be too much again for the computing budget. Finally, the subtoken performance on multiword expressions is quite subpar, as we've seen in Coptic. Our pipeline can only predict the annotation for the full token, or the MWE, so whenever we pass the subtoken, the output would not be correct. This can be solved with proper alignment, and that should be very straightforward. So, just to recap, our general approach involves pre-training a multilingual LM on the UD tokens, and then fine-tuning a multitask pipeline on the annotations. So from this process, we produced one multilingual LM on the size of Roberta, and 13 fine-tuned multitask models, one for each language. Quite good results in the test set. Majority of language task pairs outperformed the baseline, so that's quite good. And the dev set performance is also decent. Finally, all models and artifacts are available on GitHub and Hugging Face, so you can scan the QR code to see all those artifacts and the code. That's it. Thank you so much and have a great day. Thank you for listening.